Forbes and Bidelspach. They'll be talking about their proposal to do natural channel design and water-based solutions to help with water quality issues in yellow water in Ponchatoula Creek. So, do y'all want to do introductions?
Yeah, let's do introductions. We have time.
I'm Forbes with Headway and I'm out of Monroe, Louisiana, but grew up here in Hammond. And Bidelspach lives out of Livermore, Colorado, and travels the country restoring streams. And I work together a lot. And we worked with the LDEQ on this project. And anyway, Dave's gonna carry us through here.
You mind giving me your names, just since we have a small group, at least I don't know who you are.
I'm Holly with Ponchatoula Conservancy.
Ronnie, Ponchatoula Conservancy.
Tina with DEQ.
I'm Amanda, I'm a local farmer. Kelsey with DEQ.
Kindly, I work for the drainage district. Ponchatoula Creek and Yellow Water are two of my numbered laterals, so we have the responsibility to keep open and flow drainage.
I'm Ben. I work at LDEQ too, or with Tina Kelsey.
Yeah, and I know a number of these have been out to the creek, familiar with the creek. Some of these were out there, Ron, you were out with us, and we were out as well. So, we'll give you a summary of where our findings were. Basically trying to do what's called a pre-master plan and identify a project that can potentially give us a water quality benefit through the use of nature-based solutions. So this will be a summary review of the project that we worked on. So the project started. We're going to try to keep this to about 60 minutes. You see we have a lot that we want to go over in 60 minutes. We have 80 slides. I don't expect to go through every word on every slide. I'm going to give you a brief understanding of each slide, with the idea of being that if you have certain questions, you go back to that slide and give you more detail on it. So, yes.
Are you recording?
It is recording. Now.
Excellent. Okay. I can't.
You can't see it?
Online.
Okay. So, this is just kind of give a brief idea. I want to stay pretty firm to the idea of giving 60 minutes of presentation. Stop me for questions if you want, but at the end we will also have time for questions. So don't feel like you can't ask questions or you have to write them down. If you have a big question, just let me know and I'll try to answer where I think I can at that point. So as most of you probably know that we're here, this is a joint effort between Louisiana DEQ and Headway Environmental. We had two different aspects of field work on here: a reconnaissance level assessment and a predictive level assessment. Reconnaissance level assessment just says we go out there and say, hey, is there something that we want to look at and give a prediction on what might happen or what benefits we could have from that. And the predictive level is we try to use tools that are available to predict how the channel will adjust, how it will change, and what the result of that would be from a water quality standpoint. So this project was funded by EPA, funded 604B Water Quality Management Plan, part of the bipartisan infrastructure law, and it's really to demonstrate effectiveness of nature-based solutions, including natural channel design, to enhance water quality. Side benefits of this include flood risk mitigation, improved community connection, and riparian corridor improvements, as well as trying to promote community involvement around riparian spaces, and then stimulate ideas for future funding opportunities if this is a project that we want to move forward with. So trying to figure out, hey, how can we get this thing paid for in the future? What amount of land would we need? When would we need that land? When would we need the funds available for that? Is there anything else you want to have related to that, Lee?
No, well, yeah, I guess so the focus of our project that we're talking about today is to get to a point where we identify a small demonstration project. That's what this is, a new approach to try to reach attainment of the total maximum bathing loads that we have requirements. Ponchatoula Creek and Yellow Water River are not you know, they still have, are not meeting their intended uses. And some of the pollutants are nutrients and fecal coliform. It's all, you know, a couple of heavy metals. And this new program says, well, we're going to allow you now, we sent the TMDLs and we applied a round of prescriptions to try to fix it, and we're still not there. So in this new phase, which the LDEQ calls their New Vision program, the EPA says, well, we're going to open up what you can try to do because we need more tools in the toolbox. And so the new tool is how can we use nature-based solutions to try to get the water quality down to the level below that total maximum daily level. So that's the ultimate goal here is to find a demonstration project. But along the way, this project needs to actually show the community what nature-based solutions are and how they work. Otherwise, it just sounds like, you know, somebody trying to sell you something you don't know what it is. So, and that's Dave's specialty and mine, but more so his, is how do we do that? How do we get to these demonstration projects?
So the EPA will encourage us, if you decide to move forward as a community, they're going to encourage the use of a watershed plan to say, hey, we're going to meet these TMDL criteria. So that means that what we're putting together here is the start of such a watershed plan. It's not the complete watershed plan, but it's kind of a precursor for that. With the watershed assessment, we looked at the watersheds of Ponchatoula Creek and Yellowwater River, and then we looked at assessment and demonstration of river stability. In other words, we try to figure out where is erosion, where is infrastructure, where is there concerns related to erosion that we don't want the natural processes to continue on. Is there going to be a big impact if the natural processes proceed the way they are? Are there things that we can do? And of course, each stream is slightly different in how we address it. The purpose of the study is really to try to look at watershed assessment and say where is stability, where can we keep sediments from eroding into the current water courses, and while we have that sediment not eroding the water courses, will that have benefit from a water quality standpoint as well as from a stability standpoint. So we want to find these demonstration treatments using nature-based solutions, so trying to use things from nature opposed to hard engineering sources like this head wall that you see on this breach Canyon Creek. And then we're going to be talking about pre-master plan and criteria decisional analysis or multi-criteria decisional analysis. In other words, we have a lot of different goals and objectives for why we do a project. How do we put those goals and objectives together and rank them in such a way that we can say this is a preferred project? And then cost-benefit analysis. So, of the project, we had 6 major goals and 37 objectives. I'm going to go into each one of these goals and lay out the objectives for each quickly. We have a water quality goal, so we want to reduce the amount of phosphorus load, reduce the amount of erosion from the banks, reduce the amount of nitrogen going into the water, have an improvement in water quality and temperature, so in other words, reduce the water temperature so that we have lower temperatures in the water if possible. Reduce the amount of metals being exported into the water course, heavy metals that is, reduce the trash, and then increase the processing opportunities for pathogens, fecal chloroforms, and then overall reduce loading by having places for that material as it's in suspension to be able to deposit out and be encapsulated on the floodplains. And then increase the dissolved oxygen. So our first goal is really just water quality goal, and there's a lot of different objectives of how we can achieve better water quality. Our second goal is flood mitigation. This is reducing base flood elevations. We have some places that have a higher potential of flooding than others, but in general, a lot of the work being done here in the past has been done to reduce flooding. but we think that we can still reduce base flooding while not increasing velocities that would cause more erosion. We want to improve existing stormwater structures and facilities and increase flood storage in the watershed so that we reduce the flashiness of the watershed and then increase infiltration wherever possible and add buffers. Third goal is to really have community improvements. Have people get connected back to the rivers and the creeks in a way that they find them as a valuable resource opposed to just a nuisance to move water. You know, in a lot of communities, what we look at is people say, oh, yeah, there's that swamp down there, but I don't really want to do anything near there. And we want to try to incorporate ways to increase stormwater conveyance, but then also have opportunities for people to be connected to these natural spaces through blue greenways that can stimulate community excitement and repairing access through parks and spurs along those parks. Engage citizen scientist groups that collect restoration and assessment-based data through the community while doing that, and then improve recreational fishing opportunities along there, as well as people that want to do that for sustaining fisheries. The next goal is related to funding, grant procurement objectives. Anything that we do, we're going to have to get funding to pay for it somehow. So we're going to have to find ways and projects that can stimulate additional funding to come into this project. So, you know, removal of concrete and hard unneeded structures as community-led efforts. One thing that does, it excites communities, and for us to see opportunities that are not hard engineering allows for other entities to be able to come alongside and say, hey, yeah, we can put more money towards using natural materials for restoration, because we think that we can show this is a good demonstration in this community that can be used in other communities across the state and even across the nation. And then increase complexity of these projects so that there's multiple partners that can be involved and not just partners that can come from an ecosystem restoration. So in some states and some provinces that we work, there's a big push for mental health in natural spaces. So being able to have corridors that people can go to natural spaces and use it as part of mental health treatment in communities has a large correlation to a reduction in violent crimes in communities, as well as in a way of treating mental health for certain things, especially related to post-traumatic stress disorder for first responders and veterans. So in other words, allowing people to get into nature is valuable. And then the next goal number 5 and 6, is repairing improvements and objectives. We have a lot of places where we have no buffer. The stream's just a ditch line, and you know there's no place for the water quality to filter out trash, to be able to have flat places to process pathogens. So basically, we want to increase biodiversity and buffers, increase buffer widths, have plantings, allow communities to be involved in those planting opportunities, increase large woody debris and overhanging vegetation, and promote vegetation to eradicate invasive species. Now, there's questions, some of these goals and objectives compete with the stormwater-based flood level reduction is going to say have smooth vegetation so you don't raise the flood stage, and here we're saying give biodiversity. Well, that means we have to move material out of the floodways so that we can achieve both of these objectives, if that is a preferred alternative to achieve those goals. And the final one is river morphology optimization. River morphology just means how rivers move and adjust. Make sure we give room for rivers to be a river, whether it's Yellow Water River or Ponchatoula Creek or Hammond Creek. Eliminate excess aggregation, excess degradation, which I'll talk about what those are shortly. Optimize sediment transport from the bed form diversity, and then increase connectivity to floodplains or places where pollutants can deposit onto the floodplain, be stored, and not be transported downstream. All right, so I'm going to teach us all a new word. When you go home tonight, you can share this with your family or your friends, and they'll think you're really, really smart. So your new word that you're going to learn today is fluvial geomorphology. So you want to try it with me? Fluvial, geo, morphology. All right, so how many people use that in their everyday language?
I use fluvial a lot.
Fluvial, yeah, which is what? It means what?
Rain.
Rain, yeah, it's water, right? So it's
I actually learned it from you, I think.
yeah, the fluvial process. So fluvial, essentially fluvial is the act of running water. So it's what happens when water moves. That's a fluvial process. And it could be any fluid. It can also be air. It could be a fluvial process too. Geo is earth. It's kind of what the idea of what the earth's made up of. And then morphology is a form. It's kind of like Gumby down there in the corner. It's how things change and adjust in time. So this concept is really the study of landforms and the water processes that shape those landforms. It's still pretty young science. Many of the pioneers of this field are pictured in here in color pictures. So that tells you how young this science is. So it's been around for almost 100 years now as a pretty established science, but it's still young. We're still learning things about it. But essentially what we're saying is water changes dirt, then dirt changes water. And it keeps on going back and forth.
Water changes dirt, and dirt changes water.
Yeah, that's it.
Yeah,
Yeah, kind of circular, right? So fluvial geomorphology, it's based off the idea that we have streams that are steeper. When a stream's steeper, if it's made out of the exact same material as down here, you would expect more of that material to erode. So if you have a big sand pile and all this material is the same and it's steeper, then it's going to erode easier when it's steeper. As it comes down lower and gets flatter and flatter, then it's going to deposit more. So very simply, the concept of fluvial geomorphology is there's places that add sediment to landscape, there's places that transport sediment, and there's places that deposit sediment. And none of those processes are in of themselves bad, but it sure does make a difference based on how we have infrastructure planned and how we have future development planned in the region. So one of the simple things that we talk about in fluvial geomorphology is something called lanes balance. And this guy out of Colorado back in the 1950s came up with an idea that if you have more water, then you will be able to have more water here, and with the same amount of sediment, then you will have this needle move towards degradation. And degradation, sorry, let's go back. Degradation and aggradation. Degradation means below gradation. Aggradation means above gradation. Gradation means that you can have a slope on a river, and if you have water coming in, it's going to stay at that same slope, and it's what we call a graded slope. So if you're on a motor grader, you put a graded slope onto the roadway, and that slope's going to stay there regardless of how much water comes, in theory. If you're degraded, that means you're cutting down from that grade. If you're upgraded, that means you're filling in above that grade. So if you put more water onto the site and don't increase the size of the sediment at all, then it will degrade, it will cut down. That makes a lot of sense. If you end up taking less water from a site, if you take water away from the site, so in other words, you put a big dam up there and you have the same size sediment, but there's less water that gets there, then it will start to fill in with sediment and it will upgrade. So these two terms of upgraded means filling of a water course, degraded means cutting down from a water course. Natural streams are they have a natural morphology to them, which is related to this dimension, pattern, and profile. So how big is the river, how curvy is the river, and then how many pools and how much does it go up and down when you walk down the river. So you can imagine when you walk in a river, a lot of times you're walking, all of a sudden you fall into the pool, and then you come out of the pool, and then you fall into the pool, and there's this periodic nature in rivers. That's related to the profile of the river. So we talk about rivers having stable dimensions, pattern, and profiles, so that they don't have to upgrade, fill in, or degrade erode. Rivers are pretty complicated. In general, to make it really simple, there's 4 unknowns about rivers in trying to figure out how big a river needs to be, and we only have 3 equations in all of physics to understand that. Now we have other equations that we try to compare back to other streams and what are regional relationships, but in the physics and saying, hey, this is wonderful physics, Newtonian physics means that it comes out of Sir Isaac Newton's idea of physics. We only have 3 equations and 8 unknowns. So that's really hard to solve that if you remember your math from high school. You generally need to have as many equations as you have unknowns. So it means that we have to look at natural references to figure out how we can size a channel, how we can make a channel be stable in a location. When we talk about dimension, pattern, profile, dimension is really how big does the channel need to be. And this is kind of curious because if you have more rain, it needs to be bigger. But in general, rivers will adjust, and there's time that it takes for vegetation to establish. As it takes time for vegetation to establish, that area of the river becomes firmer. Therefore, the river doesn't look a lot bigger with a bigger flow because vegetation has established at certain elevations and allows for the creation of flat surfaces next to them. We have a pattern in the river, and this is essentially how curvy is the river. So as you can imagine here, right up through the interstate bridge, you can see the river cut up against one side and then cuts against the other side here. It has an area that's dry in between 2 sections, or what we call a bar in between there. This is all related to pattern, and that tells us something about the processes that are occurring in this reach. And then profile is related to that undulation of the bed. So, dimension, pattern, profile, there's days of classes that you could learn about dimension, pattern, profile of natural references. All I'm telling you is that natural streams have a stable dimension, pattern, profile that they either upgrade or degrade. One thing that we notice when we say that is that we have a primary channel that is fairly noticeable in most river courses. And this primary channel was labeled years ago by a guy named Gordon Woolman, and what he said is he called it the bank full channel. And all that means is that it's the top of the bank, and when it's full, that's what the size of the channel is. It wasn't anything super fancy. He didn't have any really big idea. He just noticed, hey, it looks like this is where the top of the bank is. That's bank full. We look at this and say, hey, how does geomorphology shows how big a bank full channel needs to be? The key is that that's where a floodplain begins. That's where these flat surfaces can begin. If you go below that and don't put enough height on there, then usually water will go out to the sides and you can't get the riparian species established because there's too much water there, too much inundation. So this bank full channel is really important when we talk about how do we restore streams, because it allows us to use natural materials. If we don't use that, we have to use hard materials, which cost a lot more money. All right, so if I was to look at this creek, look at Yellow Water River here, and I said, in time, you're going to have a discharge all the way up here at this star, all the way at this star, or all the way at this star. Which one of these stars would be representative of the place where you think the most amount of work is being done over any storm? So which one's going to be the most violent flowing water? The blue, the green, or the red?
The blue one?
The blue one, usually what we'll see with the blue one is this happens very often. So this blue one, this is like a base flow, and it's happening a lot. But if you come up here to the red one, you're going to have deeper water, and you're going to have more violently flowing water. So it's going to be doing more work when you have water all the way up here. But it doesn't happen near as often as this flow does down here. So this flow down here happens every single day. This may happen one day out of 600 days. So when you look at how much work is being done, well, if this happens every day for 600 days, maybe more work's being done here than being done up here when it only happens once every 600 days. So what the bank full stage says is it says this is the channel that does the most amount of work over time. And we go out to the field and we identify erosion and deposition, or places where we have filling and places where we have cutting. And in general, it's somewhere in between those really high flows and those really low flows is where we identify where this bank full channel is. And I only say that because we're going to be talking about.
The Patriots, the library room closed tonight at 8 p.m. All public computers will shut down for the evening at 7:45 p.m. Thank you.
I only say that because we're using this as a reference for, this is about how big the channel needs to be when we talk about bank full channel. So we would want a channel that has a floodplain that starts here so that we can get more flood conveyance, so we have more room for water to get up on the floodplain, have it slowly drain out, and have it treat the pollutants in the water. So, all right. So that is your discussion on geomorphology. Channels will start in one state and they move to different states. They cut down, then they get wide, then they deposit material or grade, and then they grow trees and they reach what's called a quasi-equilibrium state. So rivers are constantly moving. We don't have to restore a single river on this earth because every river will restore itself. We just have to worry about doing work on them if we care about what it moves when it restores itself. So as you can imagine, as a river cuts down, widens out, if there's something on top of this bank like a home, you may lose that home while it's adjusting. And rivers adjust fairly slowly in time in geologic space. Not all streams are similar. Streams are different, and because streams are different, they have different sinuosities, they have different slopes, and they have different width to depth ratios. All that we're saying here is that streams are different. So not every single stream is the same. And what is good about a stream or bad about a stream sometimes is harder to define than what's ugly about a stream. Sometimes it's easier for us to say we don't like that about a stream, not really knowing if it's good or bad. But that can be incorporated into our goals and objectives of the project. All right, so now since you're all experts on fluvial geomorphology, or at least can say the word, we're going to move on to water quality and how that is affected in riverine systems. So water quality, when we think about water quality, to make it really simple, we have a physical water quality, we have a chemical water quality, we have a biological water quality, and we have an aesthetic component of water quality. All these together are water quality. So a lot of times we won't think of aesthetics as being water quality. It's harder to put a total daily maximum load to it. But what we're going to be focusing a lot on is related to the biology and the chemistry side of water quality. But knowing that water quality includes all of this. So if we look at this picture here, what are some water quality concerns that you may have by looking at this picture quickly? Yeah, that's it. Yeah, that's a big water quality issue. You have a little bit of erosion from sediment, but the biggest thing is that you have an infrastructure that could get you. You don't know what's going to be leaking out of that. Most likely, it's probably not going to be a big deal, but that's a water quality issue.
Is that a pipe?
Yeah.
Oh, okay.
Yeah. Sorry about that. Yeah. Yeah. Brian said it's a forced name.
Well,
So
if it's sewer, if it's water, it's just water.
yeah. So this pipe that I took one that wasn't super noticeable for me one way or the other, just so I couldn't say what it was. It could be a sewer pipe. So that means it's a forced main sewer pipe, so that you force the sewer to go in one direction or the other direction towards the wastewater treatment plant, or it could just be a water pipe, a drinking water pipe, and then it sends water to it.
Is this on public land or private land?
This right here would be on the university land. So it should be state land, right?
You probably know more than
It's probably, maybe on private property, but it would be in the utility servitude if it's on
I
private
think it's
property, or it'd be
probably
on public right of way. If it's on a state highway, the state highway has 100 feet of right of way, and that pipe is, 20 feet off the edge of the road, well then it's highway DOTD right of way.
Yeah.
But utility companies don't necessarily have to do that. They can contract and pay a landowner a fee to provide a servitude for a utility. That's called utility servitude.
Does it have a lot of potential for being snagged and causing a lot of hydraulic problems?
That's probably why you see that joint right there.
Yep.
And there's probably another one on that long right there which been knocked out.
Yeah. Just whenever we have an exposed utility line, of course, as soon as it's exposed, it has a lot higher potential of causing a water quality issue than what it would be not being exposed.
Could they use directional drilling and just
They do
go
now.
underneath the channel?
That's mostly what they do.
The big point is that they didn't install it like that. They installed it underground, and the erosion has eroded down below it, and that's where the problem.
So, and right now, we will get to the point where we're talking about some solutions and we'll have questions. Right now, I just want to talk about concepts of water quality. You know, so when it comes to the idea of the water quality, you know, we're talking about could be a potential chemical problem, there could be a potential biological problem, because if this is a sewer line, and if it has a leak, it has a chemical problem, and then it can cause a biological problem because it can increase the biological oxygen demand in the creek and then cause other biological issues. It's an aesthetic problem, and then it can also be a physical problem because it causes a debris jam that will cause more erosion around the side, and that erosion will be a physics.
That's probably why you see that big washout right there, right?
That's exactly right.
That's what caused it.
Yeah, yeah. From
And if you look, the creek is dry back that way.
Yeah, yeah. And this is on Ponchatoula Creek, right downstream of the Yellow Water River cut. So just not a whole lot of water moving through this region. So a couple other things. Sometimes it's not always the creek that we think about. It's the tributaries coming into the creek. So this is on the Yellow Water River, and you can see that we have a degradation or a head cut that's forming on a tributary that's coming down the Yellow Water River. It's just a small little tributary, but it's causing a fair amount of sediment to get into the Yellow Water River and load the Yellow Water River. And the reason it's doing that is because the Yellow Water River used to be up there, well, kind of. At one point, the receiving drainage for this was up there, and now it's cut all the way down here. And it cut down that way, one, because it naturally cut down because it was confined, or in this case, because it was cut down with steam shovels, most likely, or packers back in the day. Not sure of that. But the impairments from sediment generally are total amount of solid sediments that are entrained in a water body and the turbidity. So in other words, you can have the sediment can be a problem from water quality, so it can fall in between habitats and cause problems, or it can have bad things connected to it and cause problems, or it could just be the fact that you have sediment in the water course and it makes a muddy water, and that changes the chemistry of what lives in the creek. So elementary water quality in riverine systems is, and this is very much simplified, just so that nobody had to puke about it. But we have clean sediments. With these clean sediments, and this is essentially not really saying the sediments are clean, it just means we're only thinking about the sediments themselves. They erode off a bank. When they erode, they have things sorbed to them. Sorb just means it's connected to it in one way or another. These can include nutrients like nitrogen and phosphorus or other nutrients. And they're part of the water quality chemistry problems. And then we have pathogens, which is a biological problem. So we have some sort of pathogen, whether it comes from some sort of agricultural location, whether it comes from somebody's backyard, whether it comes from a leaking underground storage tank related to septic. You have some sort of pathogens, and then you also have non-sorbed chemicals that will be transported, but it doesn't get transported with the sediments themselves. So they get transported in conjunction with the sediments, but they're not sorbed to the sediments. So this is an eroded bank. With this eroded bank, you can see that you have a steep bank. The top of the bank's right here, and as you have erosion from that bank, you have particles that will be absorbed to those eroded sediment particles, or they will be either adsorbed or absorbed. We talk about sorbed sediments. There's a slight difference in the interface of the sediment. So if you have a sediment here, if something is adsorbed, then the sediment is completely separate, and on the surface of it, you have something that's connected to it, almost like paint, if you will. If it's absorbed, then that particle moves into that sediment particle. So if you can imagine that would be like a sponge and having water that goes into it, and that's absorbing it. What we're going to talk about in this presentation is just sorbed sediments. And sorbed sediments is when geeky water quality people say, we're not really sure why it's attached to it. We're not sure it's adsorption or absorption. We just know that it's attached. So that's when we'll use that word sorbed sediments that way. One of the key, and we're not going to talk about all the different nutrients and how it absorbs sediments, but we will talk quickly about nitrogen. Nitrogen has a cycle. Nitrogen is your largest component of air, and then it will get incorporated into the soil. You have animals that die, you have animals that defecate, and then that nitrogen that comes from the decay or the defecation gets back into the soil, and then slowly biological microbes in the soil can transform that back into a nitrate, then a nitrate, and then it can get transported back into N2. So this is a nitrogen cycle. When we talk about water quality issues, not all of these components of nitrogen can be soluble in water. So we only talk about a percentage of the nitrogen that's available in the soil that can actually be transported in the water. That's all that this is meant to say, is that nitrogen can be in a lot of different ways, but not all of it gets transported in the water as a water quality thing. The fate of riparian pollutants, there's a lot of ways that pollutants can be changed in a landscape. A simple one is if you think of a farm and you have a buffer until it gets to the stream and you have cows up here, well, there's a good chance that if cows don't go down into this buffer too much and just stay on the side for shade, that when they defecate, that source of nutrients will get stuck in here in this buffer area. And these buffers form like filters. Now, that's the same in urban areas. We need buffers in urban areas for just different pollutants, but sometimes it's easier to think about it when we think about one location that could be causing this. But from a water quality standpoint, the fate of pollutants can go from encapsulation, which means that pollutant can get up on the floodplain, get deposited, and then get covered, and then it just stays there for a long, long time until it's covered. It doesn't get resuspended. It can be a filter, so we can have vegetation or other things, or even just the medium in the floodplain that allows the pollutant to filter down through and get stuck in the substrate of the floodplain that's deposited on. It increases chemical treatment times. So whenever we can have more time that you go from wet into drying to wet into drying to wet into drying, almost anything of organic nature will break down quicker the more times they can go from being wet to dry to wet to dry to wet to dry. How many people ever wear boots in the water? The more time that you wear your leather boots in the water and let them dry out, and then wear them in the water again and let them dry out, the quicker they decay. That's a basic principle of organic chemistry. The more wetting and drying you have, the more cycling, the quicker you have for decay, which can be really good for water quality treatment if you have pathogens related to sewers and septic fluids. Bioaccumulation, sometimes you can have chemicals that can get accumulated into soils and also accumulate into the vegetation. Physical settling, you can just settle out sediments onto a floodplain. Biotransformation, this means that you will have ways of change of the electron states of the chemistry, so you can go from having more or less electrons in it, which means that that material may or may not transport as easily and may stay stable in place opposed to not being stable or harming people. So that happens a lot with biotransformation of some really nasty organic chemicals like a vinyl chloride, for example. And then chemical redox, which is kind of another type of biotransformation. So water quality improvements, in general, what we find in nature is that floodplain connectivity has a real value in water quality improvement. Wetland restoration has a real value, and streams being stabilized so they don't erode has a real value in improving water quality. And they can improve them for different reasons, but the pollutants of concerns are the same pollutants of concerns, and the processes of how they give a water quality benefit are the same processes that I have just discussed before, related to encapsulation, bioaccumulation, physical settling, and chemical treatment times increases. So, if we look at floodplain connectivity, what we see, and this is not, and nobody tried to have more floodplain connectivity on this section of Ponchatoula Creek. They just reduced the amount of water. So since you reduce the amount of low flow water, we have places on the margins of these that are starting to grow as floodplain and having vegetation established just because there's less water. So floodplain connectivity means that we can have vegetation that can grow where we used to just have water because of reduction in flow. And then as we have pollutants, they can get stuck in this vegetation as they filter, and you can increase the amount of time for wetting and drying with floodplain connectivity. With wetland restoration, you increase the amount of time that water can get into, that pollutants can get into a wet area, then they can go to a dry area, and go back into a wet area. That improves the ability of a chemical process to take place to help treat or break down biological pollutants as well as some chemical pollutants. And then deposition of filters, deposition of sediment is important in wetlands where it allows for deposition. And there are a number of little pocket wetlands. This is a pocket wetland from Yellow Water River. There's a big eroded bank, but that bank had failed, and behind it, it creates a little pocket wetland, and that has some water quality benefits, just because it was created there. Not that it's a big wetland, but it can give you some benefits from a water quality treatment standpoint. And then the final thing we'll talk about is related to streams, and this is really addressing the idea of bank erosion, giving some bed diversity, and these are all related to small microscale treatments for water quality, which follow the same processes and treatments that we had talked about before. So this is these are two projects of stream restoration projects where we've changed the profile of the channel, which will change how water gets pushed through the bottom of the river. In what the bottom of the river is a place that's called the hyporeate zone. That hyporeate zone is where a lot of the biological activity occurs that will scrub pollutants from the water course. So if you allow water to kind of get pushed in and out of these areas, you can see a water quality benefit. If you have a flat floodplain, you can have water get up there, you can have a water quality benefit. If you don't see much erosion, you're not transporting sediment downstream, you're not transporting pollutants downstream, you see water quality benefits. All right. So when we tried to look at watershed screening, we looked at 41 total basins, 11 basins across the state that was provided by DWQ, 83 sub-segments that we analyzed. We had desktop analysis where we used GIS things, and we came up with 4 finalists. From those 4 finalists, we came out in April to do a reconnaissance level assessment, try to look at those different watersheds and say, okay, what do we think about this watershed? What can we use as the best demonstration? Where's a place that we think we can get people together that can get excited about this and use as a demonstration of a potential tool in conjunction with the EPA? And then the field level prediction was in June, and then from that we came up with a plan of how we could deal with restoration and a project on Ponchatoula Creek and Yellow Water River. So, one of the concepts that we talked about related to goals and objectives of community connection is related to a blue greenway. And a greenway is pretty easy. We think about greenways where people can go and ride bicycles. A blue greenway just means that it's a waterfront as a greenway. So the blue greenway would be a loop that connects Yellow Water River with Ponchatoula Creek, and then uses some of the smaller tributaries that we named as Hammond Creek, Heritage Creek, and Recreation Creek, and Z. Miller Creek, just related to names of places in Hammond. They're unnamed tributaries, but for the purpose of this study, we did name them just so we can talk about it. And these greenways have economic benefits, physical health benefits, mental health benefits, and educational benefits. But the economic benefits, as you can see in our study, there's been significant improvements in home values and real estate values associated with the installation of greenways, as well as the other benefits. So part of looking at greenways should be done from a community development standpoint. Say, hey, is this something the community wants? And if it is, are we okay with the increased property values that could come in, the potential of that? Is that something we welcome or not? We did a watershed assessment. The watershed assessment essentially goes out and says, this is how big the streams are, this is where erosion is occurring. Do we have streams that are in size, so not connected to the floodplain? What are the basic things that we can do? So we went out and we did a reconnaissance level assessment in April, predictive level assessment in June. We surveyed to try to figure out how big the channel was related to that bankful stage. We documented places of concerns of water quality. We detailed bank erosion and tried to calculate how much bank erosion would be through the reach. couple things we noticed in our watershed assessment is the drainage for the Yellow Water River is a very unique drainage. And if you can see here, you have 5 different breaches going into this node. That's a very uncommon thing in nature. So we tried to look into what was happening, and what we noticed is that as a result of the 1926 flood, for the best of our knowledge, Yellow Water River cutoff channel was constructed. So historically, if you see all of this drainage patterns, this probably had a drainage divide line that was somewhere around where my finger was at, and this was a small tributary, and this was constructed as a deep ditch to be able to bypass flood flows around Hammond so that it didn't cause flooding in the downtown region.
1926.
In 1926, sometime thereafter, yeah. Our documentation of this, the oldest documentation we have is 1939, and showed up in 1939. There's most likely the size and the amount of spoil piles on the side. This would have taken some sort of a steam engine or a steam shovel. Probably would have been done by mules. It could have been done by mules, but it would have been one of the biggest things that I've seen done by mules. So that means it's probably would have been done after 1860, and it was done before 1940.
Do y'all have any background or knowledge of that? I mean,
In 1986, a local engineer did a project to widen and deepen Yellow Water River. I had a set of plans in my office. That's in 1986.
Yeah, yeah, but that was just, and that was probably just to widen and deepen this section.
They did it in 3 phases.
Yeah.
It was back when the Department of Public Works was a state agency.
Yeah.
So it went through the Department of Public Works, but it was done by drag line back then.
Back in 1980.
Mm-hmm.
But the drag line then was probably diesel powered, right?
I couldn't tell you.
Yeah. I would imagine it would.
Yeah, I remember when that project took place.
Yeah, in 1980s. And this
This
is
was a 1983 flood, I think it was.
It probably was precipitated by that.
And
Good
Woodbridge subdivision,
Hmm?
Woodbridge,
Yeah.
they went underwater, and that's what triggered all this.
Gotcha.
To have it dredged out in 86.
86, I think, is when that project was done.
We voted on that and passed it as the parish did. We passed a millage or something here to have that done.
To have this.
And create the drainage board.
Yeah, that was, we've had our millage since the late 70s, but they may have increased it. I don't know.
That, it was an increase, I'm pretty sure.
Went to the
And
10
when they used the 1983 flood, get that millage passed and dredge that out.
Yeah.
We've done it in modern times.
Well, but this original one.
That's the original one,
Yeah.
that goes.
Because this is
in
1940. This is 1940 USGS mapping right here, and it shows this in 1940. That's what we're showing.
And in nature, in our system, you might have this in where there's bedrock that makes flow go around it, but where we have just set streams do not split and go in the opposite way. Humans did that at some point. That's what we're saying. We saw it. It was like there was some headwaters. There was a channel there because that is a drainage divide. That's the peak of a ridge between Yellow Watershed and Ponchatoula Creek. But somebody went, and it's not very far apart, that little stream that used to be Yellow Water River tributary, but somebody dug across that drainage divide and connected them before they started making maps so that they could split the flows above Hammond, which made sense, and get water around the city.
Right. And you can see here, this road, this historic road, so this is 1940 here. This historic road is very curvy compared to now it's straight. And that historic road, you have the start of a tributary here, 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 start of a tributary there, start of a tributary there. So this most likely was the divide line when they put in that roadway. And that's why they would put the road in a very curvy line.
Yeah.
It was just an easy way to put it in there. So this would have been a cut from this basin over to this basin. But the details of exactly when they did it or how they did it, if it was kind of during diesel power time, or if it was during steam power time, is something that we don't really know.
But
That's okay.
move on here,
All right, but so the watershed is basically, we have an incised channel that's been cutting down for quite a while now. And whenever we have problems, we're trying to throw hard engineering ideas at it and do them on a kind of smaller scale type project. So we're not really saying, okay, well, how are we going to address this for the entire reach? We're saying, okay, well, we're having problems, let's throw rock at it. Because it's easy to find funding to do it quickly. We have a number of reaches. This is a reach here. It's a little bit harder to see. But we have perched culverts. There's a perched culvert right there, and bridge piers that are exposed. So as you go down through here, you see a lot of hard engineering stabilization on these reaches. You see a lot of toe erosion where you don't have stabilization because of the incision. So it's trying to form a floodplain down here at this elevation where it can deposit material and stabilize the bank, but yet the top of the bank is way up here. So that's what we call incised river elevation, meaning that where it's trying to find a bankful channel to have deposition and process water and sediments and pollutants is significantly below the top of the bank. We have a lot of places of bank erosion. Those places of bank erosion sometimes are related to log jams because the bank erosion came in, the trees fell in, and they caused log jams. Other places the snags have been removed. We see bank erosion underneath herbicides and the treatment of herbicide, and then of course you have herbicide, and then you have bank erosion underneath that, just trying to keep the resistance to flow low enough so that we don't increase flood stages in through here, the herbicides. We see exposed footers on bridges. We see culverts that are significantly above the bottom of the stream. Most likely, in a lot of these cases, it's because those culverts weren't above the bottom of the stream. The stream has moved significantly and downcut significantly here. You're looking at a 6-foot downcut. We see hard engineering, some example of hard engineering that have been in place. This was a Fleximat and riprap on both sides. You know, it's stable, but it doesn't do a lot for community connection to watersheds. So it doesn't meet all the objectives that we have. And there's probably ways that this can be done with less imported rock. We see limited buffers. Some of the reaches, you just have no buffer out of it at all. Here you have a school bus for a buffer, which isn't a very good buffer. You have other places where you have streams, you have homes right up against the creek. Here's a retaining wall, but this is all encroachment into the floodplain. Most likely this home was built before anything was mapped in through there, and it just wasn't a concern, so you can deal with those types of issues. We have places where we have stormwater and roadway drainage issues and lack of buffers. We have places where we have culverts and we've had down cutting and we've lost ends of culverts from the tributaries just as the rivers cut down. We see high sediment sourcing coming from small tributaries right adjacent to the Yellow Water River and Ponchatoula Creek that's added large amounts of sediment into the system that then causes water quality impairments. We see incision and sediment loaded from tributaries of disturbances from development or just from areas that were disturbed for one reason or another. This one I think was probably from a development standpoint, where you see this sediment fan that has deposited out here where the sediment comes out. And then we see just places with high degree of incision and sediment loading. And here you have partial recovery on this bank, so you can see how high that bank is, but you have vegetation that seems to have held in there for at least a number of months of the growing season, enough for the vegetation established. So not everything's bad. This is upstream of a lot of the work that we're proposing, just trying to get a reference condition. And then even where the stream's close to opportunities for community interaction, there's really not much thought about trying to get people interactive to the creek in anywhere. It's really kind of more of an afterthought. Hey, I can get water away from us, opposed to saying, hey, this is a value to the community. So I would say they want to dig serious to recreation building, and there's a little creek in there, but it's pretty obvious when you look at the management of it, the pipes and everything else. It's not really valued a whole lot. It's just more like, hey, let's make sure it doesn't flood the recreation building. So water quality impairments based on DWQ, Yellow Water River and Ponchatoula Creek. We have problems with mercury, nitrates, phosphates. dissolved solids, fecal chloroforms. But you see that a lot of these are related to not supported designated use for N, but we also have issues related to, we just don't have insufficient data to make a reliable determination a lot too. So we have water quality impairments, but very simply, we just don't know that much about the river to know how bad it is compared to other regions. We did a reach delineation. The purpose of reach delineation is for us to try to say, hey, how bad is erosion in different places? What is the source of sediment and pollutants? With this, we have, of the total reaches, we have Ponchatoula Creek, Yellowwater River, Hammond Creek, which would be a tributary to Ponchatoula Creek. And that would be coming down in through here. And we call it Hammond Creek just because it kind of went right through Hammond. Heritage Creek, which comes by the Heritage Center. Z Murray Creek, which comes out of the Z Murray Park, and then Recreation Creek, which is a straight reach, goes right by the Recreation Building, and then we have another reach that we call unnamed tributary to Blue Greenway. So there's barely any drain there right now, but it is a drainage corridor. Of these reach delineation, some of them we walked and took pictures from the bridges, the crosses. Other ones we walked a little bit. But of the reaches in red are places that represent a very detailed assessment, trying to figure out how much bank erosion we have on a foot-by-foot basis to try to figure out what the sediment load would be on reach, and then have a calculation of the pollutant load from the reaches. So you can see that a large percentage of that, about 3 miles of the 19 miles assessed, we spent significant time trying to document how much bank erosion would come as a prediction. Now, all models are wrong, but some are useful. So even though we predicted, it doesn't mean that we're going to say this is exactly how much bank erosion is going to be coming, but it's what our prediction was. The first thing that we did to try to get an understanding of the reach is try to figure out where the floodplain is trying to develop at, or where is that bank full stage. So it's not all the way here at the very, very top of bank. We tried to survey cross sections and put together these cross sections to understand how big the channels would need to be. So if we had a channel that was trying to develop a floodplain here, the question would be, is can we put in a small floodplain that will help us with treatment for water quality, or is that unfeasible? So the first thing is create what's called a bankful regional relationship for channel sizing. So in other words, how big does this active bankful channel need to be? And we've compared this to other regions where we've done work in the southeast and other urban regions, and this is the relationship that we came up with a very minor amount of work. In other words, what we're saying is that the size of the channel is going to be related to the drainage area, or the amount of water that gets caught from the watershed, raised to 0.6 power times 21, and that will give us how many square foot the channel should be. So in other words, if you can imagine, if your 1 square mile drainage area, 1 to the 0.6 power is 1 times 21.5 means that you need a 21.5 square foot cross-sectional area. So in other words, 20 foot by 1 feet. So you can imagine 20 foot from here to that table by 150. Now, the dimensions of if it's narrow or wider can change, but that gives you a rough idea of how big the channel would need to be. From that gives us a great idea of being able to predict bank erosion. Without having an idea of how big a channel should be, we have a hard time predicting how often that channel is going to be subject to erosion and predicting bank erosion. So from a bank erosion standpoint, we went out and we modeled and we either did a detailed assessment or we looked at an assessment based on the other reaches, and we calculated the bank erosion for every single reach that was part of our assessment. So bank erosion, what that looks like is we go out and we looked at a reach and we said, hey, it looks like it could erode. We use what's called a bank erosion hazard index, which says this is what the hazard is for bank erosion. It doesn't mean that we're going to have erosion, but if there's a force applied, this means it will have a higher chance of erosion or a lower chance of erosion. In the field, what that means is we filled out these forms in the field, documented it, came up with a number, and then that qualified as this reach has a high chance of bank erosion. And if you look at it, you're like, yeah, no doubt, there's no vegetation on it, and it looks like it's eroding. And then from the near bank shear stress, which is really the force being applied to the bank. So the bank erosion hazard index is, this bank is really fragile, it has a chance of eroding. It's like this bank is made out of glass or thin balsa wood. It has a high chance of breaking. The force is how much force is being applied. So a high near bank shear stress would be like my 16-year-old boy is going to punch it for fun. It's going to break. Or I have an infant in my house and they're going to just drool on it a little bit and it won't break. So the near bank shear stress is the force being applied to the material that could possibly break. So near bank shear stress, we map that through a series of evaluations for every single one of these reaches on a detailed assessment. And then from that near bank shear stress and the beehive, it gives us a prediction of how much bank erosion we would expect to have on each region. That bank erosion would be based on number of feet of erosion per year per bank. Multiply that by how high the bank is, and by the weight of sediment, we'll give you how many tons per year you would expect to erode off of a bank. And then we look at tons per year per foot of that reach. And we have it colored by this being that the stoplight colors. If you're magenta, you're really high bank erosion. If you're red, you're high bank erosion. If you're orange, you're moderate. If you're yellow, you're still moderate, but a little bit lower moderate. And then if you're light green and green, you don't have a whole lot of bank erosion. So if you look at it, the green colors are pretty good. The red colors and the magenta colors are pretty bad. So in summary, we looked at all the reaches by region. We looked at the total tons of bank erosion. What we're seeing is that we're expecting to have 31,000 tons of bank erosion per year from these 19.3 miles of stream. That's a lot of.
Say that number again.
What?
31,000 tons.
In 1 year.
In 1 year, yes. Of soil, yeah. 31,000 tons from all these regions. That's a lot of bank erosion.
31,000 tons.
Yeah, so if you can imagine a tandem axle truck takes about 18 tons of dirt. So you're talking somewhere in the order of magnitude of 2,000 truckloads. That's crazy, isn't it? And you know, used to be I'd do all these things, but there's no way that's the case. Part of this is to monitor and go out and see if you really have that much eroded. I can guarantee you the erosion I have, the erosion number I have is wrong. But it's a pretty useful number, and it's probably in the right order of magnitude. You know, in the sense that it's just a lot of erosion. What we're seeing is about 0.3 tons per year per foot of bank erosion.
Say that again?
0.3 tons per year per foot of bank erosion, on average for all of those 19 miles. So if you think about that, and you think about water flowing up against a stream bank constantly, as we had said earlier, that little blue star, water flowing constantly, you know, that's only a couple ounces of material eroding off, or even, you know, per hour type of thing. But if you're talking about the big storms, you may have a foot of erosion loss on a 40-foot tall bank, you know, and that's where you see a lot of movement of sediment those times. And some of this erosion that we're seeing isn't accounted for in deposits later downstream. So just because we have 31,000 tons per year doesn't mean it all goes downstream. We'll get positioned in different places in the reaches, but it's all stuff that doesn't need to be part of the load into the stream. If it's not giving beneficial water quality benefits, you don't need to be in the stream. The main reason why it's there is because of the anthropogenic influences that have been applied to the past to serve other purposes. And other purposes being very good purposes, like flood protection. So they're not bad purposes, it's just we have a shift of these reaches because
That's that muddy water that we see like on fields and stuff after the stream goes down.
yeah,
That's part of that loading.
that's part of the loading, yeah. Yeah, so places
Sometimes
where,
it may be a thin crust.
yeah, and that deposition would be where it has places that are wide enough it can deposit out, and it loads up from the erosion of the stream, and then it spreads out, and then it can deposit material in the floodplain. The issue we have a lot of here, the Yellow Water River in particular, is we just don't have places for the water to deposit on the flood.
Like the big floodplains.
Yeah, we just don't have the big floodplains.
As much as we go downstream with lake water receiver.
That's it. It just goes, it stays confined, it stays channelized until it gets to a point where water can get up on the floodplain, and then it all will deposit out eventually. Or will add more water quality impacts.
So it's settling out in the lower portion, the reaches of the Alvin, off of the swamp.
Yeah, that's correct. Causes, and I can't quantify what the water quality impact is in that area, but I can tell you that there is a major water quality impact, because this would not have been a natural loading rate. There's no reason these loading rates need to be there, other than the fact that we had goals and objectives in the community, and we increased the sediment load on the reach to meet our other goals and objectives, and just didn't know any better. These things are difficult to understand. So nature-based solution, very simply, means we use things of nature and references from nature to try to treat water quality. We use materials from nature, we emphasize native vegetations, we emphasize these processes. We had 7 alternatives that we'll talk about, 1 traditional hardening, 1 do nothing, and then the rest are nature-based solutions. We can create corridors with nature-based solutions, we can have floodplain connectivity, we emphasize native vegetation. The one nature-based solution that we'll talk about is something called natural channel design. Natural channel design says, let's put back in this bankful channel of the correct size and then give a big floodplain to it. We can have a big floodplain by reconnecting to this current surface, which that works out really well if you're in a farm field and nobody lives there. It'd be a really tough one to do in hand, because you don't want to reconnect to that historic surface, because the whole reason you put in the project was to reduce flood stage for the town, so then to reconnect to that would make a lot of sense. You can have a priority 2 restoration, which means you just create a big floodplain at a lower elevation, so that you reduce flood stages, and you still have the floodplain function to deal with water quality. And then a priority 3 is basically a place where you don't have quite as much room to deal with the floodplain, so you kind of put in as much floodplain as you can because you're stuck by a bridge, a roadway, and a home. And then priority 4 is what has been being done for years. You didn't know that it has a number associated with it, but it means we throw hard rock at a site and just armor it in place. And that can be used with a lot of different materials. And there's advantages and disadvantages to each. What I want to emphasize here, trying to look at time, is that we really want to be at a place here where we can, one of the big advantages is we can enhance wetlands, have good habitat, good treatment, and we can reduce flood stage if we do something like a priority 2 restoration, which would be this idea here, create this larger floodplain. And in that floodplain, we can also create a blue-greenway trail. We can create new connections to the community. And this is being done in a lot of communities for the purpose of flood protection. And what it does is it's a nice way to be able to do flood protection work and be able to get it permitted in a way that's reasonable, because you're actually restoring the stream and getting more flood capacity, opposed to a lot of times we want to do flood conveyance work by dredging out material, dredging out sediments, and it costs a lot to move wet sediment, and it also is just difficult to get some of those things permitted if you want to do more hard engineering work. All right, so there's a number of other nature-based solutions. You can do stormwater wetlands, which is a nature-based solution using native vegetation. You can do beaver dam analogs, you do floodplain connectivity, you create oxbows. So nature-based solutions just simply means let's try to look at the way that nature treats water quality issues, and let's try to emulate that and create opportunities for nature to work long-term. So the goal is that we can put something back, have it function like that in a natural situation, and hopefully have things that are 50 to 100-year lifespan, but the maintenance is minimal because it's trying to replicate what nature does. So the more complex that it gets, there's not a big deal about it. Now, at some point, if you have so much roughness, maybe you have to go in and pull out snags again, but if you're creating a lot more flood conveyance, even if you increase the roughness, you still have the flood conveyance. Lee can, after we talk a little bit more about this, Lee can go on to talk a little bit about Harris County and some of the things that they've done on that in Texas. So one example of this is what we call 4-stage urban natural channel design. And essentially what this does is create 4 different stages for deposition and treatment of water. And it also gives you stability in different places to build and do different forms of development. So for example, even here, you could come in here and put in a sports field or something here at this stage and be just fine with it. But you wouldn't want to put a home until you came up in this location. So it's just different ways of trying to incorporate nature-based solutions into systems that are a little bit tighter with urban constraints. But here, even incorporating trails, incorporating terraces and changes in vegetation can make linear urban parks in these systems. So yes, you're having water quality benefits. Yes, long-term you're going to have more resiliency, but you're also creating a linear park with a blue greenway, which can be a huge community benefit. Especially for, one of the things that breaks my heart is there's a lot of disadvantaged communities that are taught that you stay away from places of nature because of the risks associated with that. So the more blue greenway trails that we have, the more connection we have to get people from all different communities and ethos to be able to be interacting with natural spaces and valuing natural spaces. So here, one example here would be, this is a project we're doing in Pritchard, Alabama, in a community that doesn't have much connection to nature. It's just a concrete line ditch. Remove the concrete line ditch, put in a nature-based solution is what we proposed, and then with that a blue-green bike trail. This is just a greenway bike trail we're doing there just because the flows are smaller. You're not going to have a shoreline. It's a smaller range. It's 8 CFS instead of but in urban channel design, one of the things that we want to emphasize is that the elements of a stream corridor in urban is geomorphology, which I really like, and hydrology, which I think as engineers we understand. It's vegetation, but it's also this community and value. It's this idea of connecting communities back to nature, and that's a big part of what it looks like. So we have 7 alternatives related to nature-based solutions. And we created what's called an MCDA. An MCDA is a multi-criteria decision analysis tool. What it does is it takes our goals, from each one of our goals, it lays out the objectives for those goals, it ranks them based on a score, and then each alternative, we look at it and say, hey, this is better than this alternative to meet that objective, and we just score it. And then it sums the totals. The highest number gives us the best score and says that this, based on our goals and objectives, as we assumed, this is the most optimal for that. So it's really hard to see here, but if you can imagine that we have a water quality goal and we want to have a pathogen and fecal reduction. With that pathogen and fecal reduction, if we have a big floodplain treatment, we're going to have a 5 associated with that. Because with that floodplain treatment, the water spreads out. If we do a priority 4, we end up just getting a 2, or we don't get much treatment because the water can't spread out much. So we don't get much treatment. So from this MCDA, and it's in our report if you want to read it in more detail. This would take a long time to go over in detail. What we show is that our preferred alternative for treatment when possible is this idea of this 4-stage urban channel design. So creating these flood corridors and having them. Now that doesn't mean we can always afford it. It doesn't mean that it's always what we're going to do. It just means that for the goals and objectives of projects, where possible, that's what we'd like to do. So, and it's not super close in the sense that we have 601 points here. The next closest is 588 points there, and then we have other alternatives that aren't very close at all. Like so, you're only half the number of points for a priority 4 restoration using nature-based materials as a 4-stage urban channel. So this is just to show you that there was an idea of how do we prioritize restoration for the goals and objectives of this community based on our assumptions. Now, if we move forward with a watershed master plan, we also want to look at what the goals and objectives that we assumed are compared to what the goals and objectives of the community is. And that would be something that would be a task that we would give these goals and objectives almost like a straw man to people in the community. They'd say, well, I don't really think there's much value in that. I'm not going to rank that really high and let people be involved in that range. This is a big project. There's 19.3 miles that we looked at. It's going to cost a lot of money. To be able to move forward with it, we're going to need demonstration projects and locations to help build excitement in the community and see if there even is excitement in the community. I mean, if you do a small project, nobody cares, and people are, that's a big waste of money, we don't want to be involved in that. Well, then you better find another way that you can find value in this, because we're not getting enough excitement from the community to suggest doing a bigger project. So we want to look at demonstration projects. Sometimes that's just building connections with local contractors. Sometimes it's giving training opportunities for people to learn how to do construction in different ways. This was inmates that we were teaching how to do construction. Other times it's how to do design. So there's value in these demonstration projects in the community. But if you can imagine that if we can train inmates how to operate construction equipment to build stream restoration projects, I can guess that there's a lot of contractors in this area that we can train how to do this work, and you can have local contractors be doing this work as well. So it should be something that could be a potential work project for the community, by the community, opposed to being something that, hey, you have to bring in special people from out of town to do. River structures, they're somewhat complicated. We want to use natural materials, but it doesn't take that long to teach somebody how to build these things. A lot of these structures are built. If you have a contractor that can use survey-grade GPS, you can build these into the surfaces with survey-grade GPS. So it's not, although there's complexity in river structures and they have function, we want them built correctly so that you can have a sustainable project. It's not impossible to teach people that don't have much background in how to do this. Stormwater best management practices and tools sometimes are a little bit more difficult because they're more hard in engineering than the nature-based solutions, because we are stuck in a curb fitted on a parking lot or something. So we want to build things that are a little bit more difficult. So the stormwater BMPs are more of an engineered tool, but they're also being done in the community at different levels. So even though you're not, you have contractors that can do curb cuts. You have contractors that can do curb and gutter. You have contractors that can put in a drop basin. So those things can still be done as well, even though they're a little bit unique. They can still be done locally. So to give you a rough idea of the initial cost that we're looking at is if we were to do as the Cadillac grand idea of this Blue Greenway Trail and flood stage reduction and water quality treatment, we see 19.3 miles of some form of restoration. And our rough estimates are that it's a $56 million project. That's an expensive project. And if we want to continue on that, finding funding opportunities are going to be really important. I can guarantee you that the money to do this is probably going to be able to be available if the community wants to do something like this. But we can't go into it thinking, hey, this is going to be kind of a cheap cost. The first demonstration project will be cheap, but the whole project is going to be costly if we want to see a water quality improvement. The water quality improvements that we're looking at are on an annual basis. We're looking at 27 tons per year of clean sediment reduced from the watershed. That's a lot of clean sediment each year being reduced from the watershed. Now that doesn't mean that erosion is going to stay growing at the same rate every year, so we may have a reduction in erosion. But on average, if we have a 100-year lifespan, we're talking about $21 per ton of clean sediment removed. When you look at that over a 100-year period, I can guarantee you in 100 years it's going to cost you a lot more than $21 per ton to move clean sediment on average. So is there value in it? If you want to keep that sediment out of downstream reaches and out of downstream basins, then there can be a lot of benefit in doing it now and stabilizing things, opposed to allowing the river to just take its course. And the river takes its course, it's going to go wider, it's going to go deeper, and there's going to be more infrastructure concerns associated with it. Just like the mill levees that you had to do in the past, sometimes you have to come up with a program and say, hey, this is how we're going to move forward for future generations. And you guys have great examples of being able to have done that at a level in the past, but this is a big level. But it's also a big level that can be done in the community. So if you said, hey, this is something we want to do as a community, and you say, hey, we have a 20-year plan for how we're going to achieve this, then that money can go back to the community for 20 years, and then every year you can go after a new project, a new phase of the reach, go after new grant funding, go have changes in administration. Some administrations will say, yeah, we want to be a part of this, and we really want to push money this way. Other administrations will say, that's not really our interest, but things will change. And then you'll be able to find people that want to come alongside and fund this. And then long term, what you're going to have is a sustainable system that you're giving to future generations. But it's costly, it's not cheap. What we'll see is that we'll have a reduction of total nitrogen, total phosphorus downstream. These seem like fairly small numbers, 10 tons per year, 14 tons per year. But that 14 tons and 10 tons per year can have a huge effect on algae blooms. It doesn't take that much nitrogen or phosphorus to be out of sync with the system. Usually you're talking about parts per million of nitrogen or phosphorus, not tons per year. A part per million is 1 milligram per liter of so one milligram per kilogram of water. So you can imagine 1 little milligram of nitrogen in an entire kilogram of water. All right, so we're going to talk about 4 demonstration projects. I'm going a little bit late, and that's the end of it then. First demonstration project is at the Yellowwater River cutoff and diversion. So this is where the Yellowwater River was dug out in the past, and this is where Ponchatoula Creek was. So the Ponchatoula Creek went around here, flooded Hammond, and then they put in this diversion channel so they went across the divide and we reduced the staging here. Right now you don't see much water base flow that goes down this way. Almost all the base flow goes down the Yellowwater River. What we're proposing is to basically still take a lot of the flow down the Yellowwater River, but be able to still push base flow down through Ponchatoula Creek. So it won't affect the flood flows in Hammond at all, but the base level flows, you'll actually see water in these sections of Ponchatoula Creek, and will have a real benefit in the community where people can actually see a creek come down through there, opposed to right now it's kind of dry bed. So it doesn't mean that seasonally it won't dry up, but it would have a change in that. And with that, we also have enough room for corridors and stability on the floodplain. That's 1.2.
The library will close in 5 minutes. If you have any items to check out, please make your way to the circulation desk.
They locked us in 5 minutes?
Otherwise, please make your way to the exit.
5 minutes.
Since we do this,
We gotta be outside in 5 minutes.
we will reopen
Demonstration
tomorrow at
project
9 a.m. Thank you.
Demonstration project 3 is removing some armorings to show that you can use this through nature-based solution. And the 4th demonstration project is really the idea of trying to